We will continue with another example of linear momentum, and for this one it is an open system where the system consists of water jets starting from the inlet port into the outlet points. Okay, so a question like this, a water jet hits a conical deflector. So this is the deflector. Okay, and if you can see from here, we have the same angle, 50 degree on top and bottom. Okay, horizontally and deflects to an angle of 50 degree as shown in figure question 4a. So this one, estimate the anchoring force Fry and Frx required to hold the deflector from moving if the velocity of the water jet remains constant. Okay, so there are a few important things that we need to know here. First, this is happening at atmospheric condition, meaning over here, pressure at this point and this point and this point should be equal to 0. So we just assume this is point number 1, this is point number 2, and this is point number 3. Okay, so this is the conical deflector. Okay, and this is ATM pressure, meaning at this point P1 for this question, P1 should equal to P2, should equal to P3, and equal to 0, because everything that we do over here is at an atmospheric condition, because P1, P2, and P3 is gauge pressure. Okay, so next we need to identify a few things here. First, we need to draw the forces. So this one, P1A1 should be moving that direction, P2A2 should be in this direction, P3A3 should be this direction. I know P1, P2 and P3 should equal to 0, but by doing this direction over here for the force, at least we have we train ourselves to draw the forces direction correctly. Okay, and then next we draw the momentum direction, m dot v1, and then this is m dot v2, and this is m dot v3. Okay, because we have different mass flow rate, it is given here. The picture separates into two 50 degree angle theta. It means mass flow rate over here, here and here should not be the same. So we can assume, so this is mass flow rate of point 1, this is mass flow rate of point 2, and this is mass flow rate at point 3. So what we can do is mass flow rate at point 1 should equal to mass flow rate at point 2 plus mass flow rate at point 3. Okay, since both of them, okay, is having the same angle, 50 degree, okay, and the velocity is the same here. Here this is 10 meter per second, this is also 10 meter per second. We can assume that m.2 and m.3 should be equal to each other. Okay, so I do m.2 should equal to m.3. Okay, and because of that, it is like doing m.1 equals to m.2 times 2. Okay, so to find out what is your m.2, it is equal to m.1 divided by 2, and if you want to find out what is m.3, it is equal to m.1 divided by 2. Why? Because as I said just now, m.2 is equal to m.3. So what happened here? The mass flow rate here should be twice the mass flow rate on point 2 and point 3. In order for us to calculate the Fry and Frx, so we do the separation again. This will be force and momentum. Okay, so for force, we do summation of force equals to 0 for x direction. So we know P1A1, P2A2 and P3A3 should equal to 0 because the gauge pressure is 0. So we can just put 0 plus FRX. We assume it's going to the right as usual. For the momentum, we need to remember the momentum is always m dot V outlet minus V inlet. Okay, so for this case, we have 2 outlets and 1 inlet. Okay, so we need to separate because the outlet and inlet is having different mass flow rate. So because 2 and 3, the mass flow rate is the same, we can just do equals to m dot 1 divided by 2 because the definition of m dot 2 is equal to m dot 1 divided by 2. And then we have V outlet to be positive to the right, V2 cos 50 degree. Okay, and then we have plus V3 cos 50 degree because both of them are moving to the right based on this arrow. And then we minus the mass flow rate for the inlet, m dot 1, and this should be multiplied by V1. Okay, remember the question say the velocity remains constant, so V1 should be equal to 10 meter per second also. So if you put numbers for this question, FRX is equal to m dot 1, which is just now we have Q 0.02, so this is water, 1000 times 0.02 divided by 2, and then we have multiplied by V2, which is 10 cos 50 plus 10 cos 50 minus m dot 1, 1000 times 0.02 multiplied by V1, which is also 10 meter per second. So for FRX, and the answer for FRX is equal to negative 71.44 Newton. Okay, so that will be the FRX. For FRY, summation of Fy equals to 0. We also know this is 0 minus W plus FRY. We don't have any estimation for weight, so this is also 0. And it is equal to m dot V outlet. So this is m dot 1 divided by 2. V2 sine 50. Okay, and then this is going downward, minus V1 sine 50. And then we don't have any calculation for here because m dot V1 is direction is going to the right. Okay, so we don't have any y direction for m dot V1, so this is equals to 0. Okay, so FRY will equal to m dot 1, 1000, 0.02 divided by 2, and then multiply by V2, 10 sine 50 minus 10 sine 50. Okay, this cancels each other, becoming 0. So FRY should equal to 0 Newton. So that will be the answer for this question. Based on the answer shows that we only have FRX condition, which is negative 71.44 Newton. It means for FRY we don't have any movement for the deflector, if the flow is moving this way, it hits the deflector, it will not move to the top or to the bottom of the system, but it will move to the right. And in order for us to overcome the movement, we have an anchoring force of Frx moving to the left. So that's why the answer for this question is negative 71.44 Newton. So this is the Frx. That's all for this question.